So the last case is what? So the last case is the GCD of Mn is not 1, it's not 0. So it is like the third case or the symmetric case. Let's say the GCD of M and N, let's say this is equal to P, because N has only 2 prime factors. So the GCD is either equal to P or the GCD of Mn is equal to Q. Is that okay? Either P or Q. N is the product of 2 primes. Okay? But then if you can prove this one, then this one is symmetric. So this one we don't need to do. So this one is by 3. We get it. So how about this case? Okay, so that means M is divisible by P. So we get what? So we get, so C to the power D is equal to M to the power ED, and it is equal to 0 mod P. So we know. And then C to the power D is equal to M to the power ED. So 4, let's see I have, whether I have space or not, which is equal to M to the power K phi N plus 1, right? So this is equal to, so I copy things. Okay, so this is going to be, so let me copy this thing first. Okay, so this is going to be M to the power K Okay, so here, so we are looking at the third case. So in this case, so first of all, instead of looking at mod n, modulo n, let's look at some more basic, modulo p and modulo q. What is going to happen? So first of all, we will find that the value of m to the power ed is going to be equal to 0 mod p, right? And then if it is equal to 0 mod p, then this is going to be equal to m mod p. Is that okay? Because m is the multiple of p. The other case, let's take a look of m to the power ed mod q. What will happen? So m to the power ed, let's write it down again as this one. So it is m to the power k phi n m, right? And what is phi n? It is multiplicative. Phi is multiplicative. So this is equal to m to the power phi q k phi p. Am I correct? Times m. Is that okay? Now when we look at modulo q, m to the power phi q will be 1. So this becomes 1. 1 to the power something. 1 times m. Okay? Now, we find out that although this is not the same as case 2, we still have something similar. We still have something what? So after this, we can conclude that if we have the message c to the power d, if you minus m, because c to the power d is equal to m mod p, c to the power d is equal to m mod q, c to the power m is divisible by p and q. Is that okay? Is that okay? C to the power d minus m is, because c to the power d minus m is divisible by p. C to the power d is minus m is divisible by q. C to the power d minus m is a multiple of p as well as q. But p, q are coprime. So it is divisible by p times q. And what is pq? PQ is n. Is that okay? So we get the same case. Then in that case, c to the power d minus m is a multiple of n. So c to the power d is equivalent to n. So that we have. Okay? So in every case, no matter what the original message is, if you raise it to the power e and then raise it to the power d, then you get back to yourself. So this is something amazing. Okay? Okay. So let's try to get the scheme by ourselves. Let's try together, okay? To do the setup and everything. Let's try and see what we will encounter. Okay, so let's try to do the setup together. Okay, so let's try a setup. So we want to choose what? Choose 2 primes p and q, right? Okay, so let's choose, example, let's choose p is equal to 7. Q is equal to 11. Is that okay? Is that okay? So we get n is equal to what? 77, right? Okay. So we want to pick a number e. Pick any number e. Okay, so here for me, let's say we have e as the example, 7. Okay. Usually, e could be a small number. Okay. Well, maybe not that small. Okay, let's, for our example. Why do we want to choose 7 again? Yeah, whatever. So it doesn't matter whether e and p are the same. It's okay. The criteria of finding an e is e should be co-prime with phi of n. So we need to find out what is phi of n. What is phi of n? What is this? Look at 77. It is difficult, right? But if you look at 7 and 11, that's easy. It's like p minus 1 times q minus 1. So it is 60. Is that okay? So we can choose e is equal to 7. Okay. Now this is enough for the sender. Sender just needs to know this 7 and what? 7 and 77 and can send the message. Okay. But for you, you want to do the decryption. You want to find a d such that e times d is equal to 1 more 60. So how can we find that? Wow. Well, you can do that by trying one by one, but that's a much easier way to find out this. We can use, so this is like what? Why do we know ed equals to 1? There is a d exists. Because the GCD of e and 60 is equal to 1, right? There must exist some number such that e times d is equal to 1 modulo 60, right? So the key here to find the d is, let's use Euclidean algorithm to help us to find this one. So we are going to use a special form of Euclidean algorithm. So we usually call it the extended Euclidean algorithm. Extended Euclidean algorithm. So it's exactly the same as Euclidean algorithm, but you store a little bit more information. So in Euclidean algorithm, you start with 2 numbers. One is the 7 here, and one is the 60 here. Is that okay? And then you want to get to the GCD. Okay, but here, for 7, I will represent 7. Extra information, 7 is what? 7 is 1 times 7 plus 0 times 60. 60 is 0 times 7 and 1 times 60. So I'm going to represent each number here with a representation, with a linear combination of 7 and 60. So when I do this, you will know what we are going to do. So when you look at the Euclidean algorithm, so you are going to deduct as many 7 from here as possible, right? You can deduct what? Deduct 56, am I correct? So we are going to deduct 56 here. So when we deduct 56, you get a 4. Am I correct? So what is 56? 56 is 8 times of this one, right? So if 7 is 1, 0, 56 will be 8, 0. Is that okay? Does that make sense? And then in that case, what is 4? 4 is this one minus this one, right? 4 is this one minus this one. So it is equal to minus 8, 1. Is that okay? Does that make sense? Okay? And then you have this 4. You are going to deduct as many 4 from this as possible. So you have a 4 here. And then you get a 3. Am I correct? So what is 4? 4 is minus 8, 1. So when you deduct this, then you have 9 minus 1. Is that okay? Does that make sense? And then you want to deduct 3 from this one. And then finally, you get a 1 that you want. Yeah? Let's check it later. So what is 3? 3 is 9. Did I make a mistake? Yeah, let's try. Is it? 9 times 7 is 63 minus... Yeah, it looks correct. Okay. 9 minus 1. Am I correct? Somehow this is... Oh. Okay. So you get a 1. 1 will be equal to minus 17 and 2. Is that okay? Is that okay? So good. Then you know what? Minus 17 times 7 plus 2 times 60 is equal to 1. Let me copy it. Minus 17 times 7 plus 2 times 60 is equal to 1. Okay? If you are going to take modulo of 60 on both sides, then you will have minus 17 times 7 is equal to 1 modulo 60. So you get this one is minus 17. Is that okay? But if you want a positive number, then, okay, make it positive. You add 60 back, okay, because minus 17 and minus 17 plus 60 is the same, so this is going to be 43. Is that okay? So we can use 43 by ourselves as the secret, the key that we should hold in our hand. Okay? 43, is that okay? Good. Okay, so this, now, let's do one more example. Okay, so here, so we are going to do encryption, right? So when we are going to do encryption, we have a message. Let's say the message here is what? 4. Okay, so suppose that the message here is 4. Okay, then we want to compute the C which is equal to 4 to the power 43. How do we get this? Okay, so you can multiply 4 by itself 43 times. This is one way. So it takes 43 steps. Okay, but you can do it a little bit better. So because 4 times 43 is equal to what? Is equal to 4. So what is 43? 43 is equal to what? 43 is equal to 30. So let's take a look at the binary representation of 43. So 43 is equal to 32 times plus 8 plus, is it? So this is equal to 43. So what we are going to do, we try to get 4 mod. We try to get 4 modulo our n. What is our n? N is 77. We get this one. So we can get this, right? And then you get this number, you square it. The square of this number, you will then get 4 square modulo 77. Is that okay? Is that okay? And then you have this number, you can get the square of this number. So you get 4 to the power 4. And then you have 4 to the power 4, you can get 4 to the power 8. Is that okay? 4 to the power 8, you can get 4 to the power 16, and then you can get 4 to the power 32. Is that okay? Now, once you have all these numbers, 4, 4 squared, 4, 4, 4, 8, 4, 16, 4, 32, okay, you select the numbers that you need to get 4 to the power 43, multiply them together. That will be the C that we want. Does that make sense? Does that make sense? Okay? Okay, but this one, is that okay? So what one way to do is we create an array. So the first entry, you store 4 to the power 1. The second entry, store 4 to the power 2. The third, 4 to the power 4. and then 4 to the power 8, 4 to the power 16, 4 to the power 32, and if it is necessary, you get 4 to the power 64, and so on and so forth. And then you look at the number, 43, you get the binary representation, you know which part is needed. You multiply the corresponding parts, and then get what you want. Is that okay? Now, but there is, so this one needs an array, but it takes roughly order of log of this number of steps, like log E steps. This is E, right? Log of this number of steps. But there is another way that you can avoid the use of the array. Okay, this is very cool. Okay. Look at the binary representation of 43 again. So it is like 32 plus 8 plus 2 plus 1. Is that okay? So this is the binary representation of 43. Is that okay? Okay. Now what we are going to do, we are going to scan this from left to right. Left to right, not right to left, left to right. Okay. So you start with some number, let's say C that we want. So but C, let's start with 1 at the beginning. Okay, now when we are, so we are going to scan this one by one. When you look at this number, okay, if it is a 1, then you multiply by 4. Okay, you make it 4. The 4 is the message, multiplied by m. Okay. Now, when you go to the next number, you are going to square it. It becomes 4 squared. Is that okay? If it is a 0, you are done with this round. If it is a 1, you further multiply by 4. Is that okay? So this is what happens after scanning the second one. Is that okay? After, when we process the third one, we are going to square this number, make it 4 to the power 4 squared, right? And because it is a 1 here, you multiply 4 here. Is that okay? So this is the number that we have. And then this number is exactly equal to 4 to the power 5. Is that okay? When you process this, this is a 0. So you just square it. Okay, so you have 4 to the power 5 now, then you have 4 to the power 10 here. You look at this number, this is a 1. You square it, so you get from 10 to 20. But there is a 1. So 20 to 21. Is that okay? Is that okay? And then this one is done, you get 4 to the power 21. And then when you look at this number, you square it, 21 becomes 42. And then you multiply 4 again, you get 4 to the power 43. So each time you move right-hand side, you square. And then if it is a 1, you further multiply 1 more m. Okay, and then you can check that it's exactly what we want. Because whenever we, so at the beginning, we have a 4 here, right? And then here, we get 4 squared. So if we do not know how long is this number, then we stop here. Then if the binary representation is 1, 0, then we should get 4, 2. Then when you have 101, then you have a square of this number and then multiply it by 4. So you should get 4 to the power 5. So when the binary representation stops here, 101 is exactly 5. And then this is what we want. And then this one, 4 to the power 10. You square it. It is because the index is multiplied by 2 by padding a 0. You square it and further multiply by 1 time. It is because if you shift 1 position and add a 1 here, you are making the index 2 times and then plus 1. Is that okay? So this is how it works. So for this one, you will get 4 to the power 43 in the end. Is that okay? So using this scheme, you still take log of the size of the exponent, number of steps, log of these 43 steps. But then you don't need an array. Okay, so this is called the exponentiation by square and multiply. You can think about something like this. Okay, but this is a strategy that is used in multiplying polynomials. So there is a way to do the polynomial evaluation using this way. Okay, and once you have this one, so you get 4 to the power 43, let's say, and amazingly, okay, this is going to be equal to 60. Yeah, we are using this number. This coincidence only. So this is going to be 60, but mod 77. Is that okay? And then when we do the decryption, you look at this 60. You use this 60, and then raise it to the power. oh, I make a mistake. Okay, I make a mistake. So whatever. So this one, it should be 7, right? So I'm doing, okay. So here, somehow some people computed, okay, so here, this is decryption, okay. But the scheme, I hope you get what we want. Okay, so so we are doing the decryption, and we actually have a message C here, and then we compute M back here. Okay, sorry. Okay, is that okay? So whatever encryption or decryption, we are using the same strategy, exponentiation. So we can use this scheme of square and multiply in the same way. Okay, that's all. That's all for today's. So next time, okay, so for this topic, yeah, there are some miscellaneous related work here. You can check up the notes. But next time, when we meet on Thursday, let's talk about a new topic, the group theory, the introduction to group theory. And it is related to this thing. Okay? Okay, thanks. Okay.